All right, this is chapter 2, Compute Services, the Engines of the Cloud. In this chapter, we'll explore the compute backbone of Google Cloud Platform, the tools that power everything from the simple web applications to global scale machine learning jobs. And we'll focus on 4 areas: Compute Engine, App Engine, Kubernetes Engine, and Cloud Functions. Each of these services serves a unique purpose, and together they offer developers and organizations the flexibility to run applications the way that best suits their needs, whether that's virtual machines, containers, or event-driven code. All right. Compute Engine, virtual machines your way. Imagine having a data center in your pocket, or better yet, under your full control across the globe at the click of a button. That's exactly what Compute Engine offers you. In the Google Cloud ecosystem, Compute Engine is your go-to for infrastructure as a service, IaaS. It's like running a virtual data center that you can fully configure, control, scale, and automate, all while running Google's global infrastructure. Your virtual machine, your rules. Within Compute Engine, with Compute Engine, you're spinning up virtual machines, VMs. These are software-defined computers that run in one of Google's globally distributed zones. These VMs behave just like physical machines. You choose your operating system, your CPU and memory configuration, and your disk layout. Then you deploy applications, run services, or launch batch workloads, exactly as you would on premises, but without the overhead. Want to run a Windows workload? No problem. Compute Engine supports Windows Server 2008 R2, 2012 R2, 2016, and new versions. Prefer Linux? You're covered with the following choices: Red Hat Linux Enterprise, RHEL, Ubuntu, Debian, SUSE Linux, and CentOS, and Google's own container optimized OS. These VMs are deployed inside virtual private cloud, which provides a secure, isolated networking layer, giving you control over firewalls, IP ranges, routing, and the DNS resolution. Disks and storage. Every Compute Engine VM comes with a persistent root disk by default. This disk behaves like a traditional boot drive. It can be expanded upon with additional block storage volumes. GCP's persistent disks offer high availability across hardware failures, encryption at rest by default, options for standard HDD for cost savings, or SSD for performance. And here's the magic. You can resize disks on the fly and detach and reattach them across VMs. The flexibility makes Compute Engine ideal for use cases like running legacy custom applications, hosting high-performance databases, deploying CI/CD runners, building render farms, or handling GPU-intensive machine learning pipelines. VPN types match power to purpose. Google Compute Engine doesn't believe in a one-size-fits-all approach. You get to pick from machine types that fit your workload. This is E2, N2, N2D series. These are balanced for general purpose computing. You have the C2 and C2D series, which are high performance and compute optimized. You have the M series, which is memory optimized for massive in-memory workloads. You have the T2D Tau VMs, which are cost-effective, bursty compute with high performance per dollar. And you have the A2 VMs, powered by NVIDIA A100 GPUs for machine learning and HPC. For startups, testing, or ultra-light workloads, there's also F1 micro and E2 micro instances, perfect for dev sandboxes. Tip: GCP machine types support custom configurations too, so you can dial in the exact number of vCPUs and gigabytes of memory to suit your application and avoid overpaying for resources you don't need. Images, snapshots, and templates. Virtual machine image is the blueprint for your VM. It includes the operating system, installed software, and configurations. You can choose from public images maintained by Google and open source communities, premium images like RHEL, that Red Hat Linux, or Windows Server with licensing built in, custom images. You build your own image either from scratch or imported from on-prem. If you want to standardize deployments across your team, use instance templates. These save every setting, from boot disks to tags, allowing you to spin up new VMs with one command or through an autoscaler. Snapshots allow you to back up your disks, and this is perfect for cloning environments, migrating regions, or restoring after an update gone wrong. Dynamic features for real workloads. Compute Engine offers dynamic operational features tailored to enterprise needs. Live migration. Your VM stays running even during Google's infrastructure maintenance. GCP moves your VM in real time without downtime. Note, this does not apply to VMs using GPUs. Preemptible VMs. Think of these as deeply discounted, short-lived VMs, perfect for stateless or batch workloads. They're up to 80% cheaper, but can be shut down anytime with a 30-second warning. Sole tenant nodes. For compliance-heavy or performance-isolated workloads, you can reserve physical hosts that only your project uses. Shielded VMs. These are hardened virtual images that include secure boot, virtual TPM, and measured boot to prevent rootkits and unauthorized modifications. In your VM workload, here's what a typical deployment looks like in GCP. You go to the compute engine, which we're at, you go to the VM instances, and you click create instance, which we just did. You can choose your name, which we have here. This goes for year, month, day, time, right? Choose your name, machine type. Let's see the region. We'll choose Iowa. Zone, choose 1A. Pick an OS image. E2. We define the boot size and disk. See 4 vCPUs, 16 gigabytes. That's nice and small. And then, excuse me. All right, come on. All right, the CPU platforms, 2 per core. No, we don't need that. General purpose. Okay. Networking. All right. We can set our firewall rules, HTTP traffic, HTTPS traffic, load balancer health checks. And then let's see, observability. We can install agents for monitoring. We can enable display device. We can turn on secure boot. We can turn on TPM, trusted platform module, integrity monitoring, metadata, and then we can hit create, right? Which we're not going to do. So you can script all of this using the G Cloud template and instances using this command. Oops. I don't know why that did that. Give me a moment for it to poke. Oops. So you could do G Cloud compute instances create and then name it. Just back. And then this asks me for my zone. Yes. So I use gcloud compute instances create and then the name. All right. So this output, the name that we just put here in that zone mentioned here in one standard. Here's the internal IP, the external IP, and now it is running. And you see that here. Okay. And we're going to close that out in a moment or two. Next up, we're going on IAM. All right. Every compute engine VM is integrated into Google's identity and access management system. You can assign IAM roles to control who can start, stop, or delete VMs, restrict SSH access using OS login, limit service account scopes to enforce least privilege. And each VM can run under a service account, giving it access to the GCP services securely, like writing to cloud storage or querying BigQuery without needing to store API keys. Okay. Common use cases. Let's wrap this section with a few examples of where Compute Engine shines. Bioinformatics workloads processing terabytes of genomic data, rendering farms for animation studios scaling out across hundreds of preemptible VMs, firewall appliances or VPN gateways requiring custom networking stacks, lift and shift legacy enterprise applications such as SAP or Oracle, running it in secure, scalable cloud environments, remote development environments spun up per developer, per branch. Compute Engine gives you the ultimate control with none of the rack and stack hustle. So to recap, Compute Engine delivers customizable VMs as infrastructure as a service, supports a wide range of OS images, machine types, and storage, and it's designed for high availability, performance, and enterprise security. It automates provisioning via templates, scripts, or APIs. Perfect for workloads that need full control or that can't be containerized yet. And that's the beauty of Compute Engine, a virtual server platform designed for scale, agility, and deep customization, running on one of the fastest, most reliable networks in the world. VM types, the power to match every purpose. When it comes to choosing the VM types, let's close this. This is Okay, when it comes to running this, every application is different. Some need muscle for number crunching, others need memory to store vast in-memory data sets, while others are just light background tasks. That's why Google Cloud provides a variety of virtual machine types tailored to your workload, your budget, and your performance goals. Let's break them down. Standard machines, the all-around performer. If your workload is somewhere in the middle, not too heavy or not too light, standard machines are your go-to. Let's go back to this. The VM types are designed for general purpose computing. You see it here? They strike a balance between the CPU and memory and are ideal for web servers, business applications, small to medium databases, development and testing environments. The E2, N2, and N2D families offer varying levels of flexibility and performance. E2 is cost efficient and great for budget conscious applications. N2 and N2D offer better performance and scalability. Exam insight. Here's an exam insight. E2 VMs offer dynamic resource management, meaning Google may shift the host behind the scenes to optimize utilization, but your app continues running uninterrupted. High memory machines. Okay. Okay, so let's say you're running an in-memory cache, a large-scale relational database, or a real-time analytics engine. In these cases, you need more RAM per vCPU. This is where high memory machines come in. These VMs provide more gigabytes of memory per virtual CPU than standard options, perfect for apps that prioritize memory over compute. Common use cases include SAP HANA, Memcached Redis, BigQuery connectors, Java-based enterprise platforms. They come in varieties like into high mem, M1, M2, ultra high memory machines. The latter scales to 12 terabytes of RAM per instance for memory workloads. Let's see. These are M1, M2, and I don't see the N2 here. Into high mem. I don't see that here. No. Well, it's not. I must have to. I'll have to request that. M2 Mega Mem. M2 Ultra Mem. M2 Hyper Mem. Maybe they retired it. That's okay. High CPU machines. These are compute optimized, right? These are for the number crunchers. Now, imagine you're running batch jobs, like batch jobs, video rendering, machine learning inference, or high frequency trading applications. You want maximum compute performance, but not necessarily memory. This is where high CPU machines shine. These VMs offer more vCPUs per gigabyte of memory than standard machines. They're optimized for scientific simulations, image and video encoding, CI/CD build farms, containers doing math-heavy tasks. You can choose from predefined high CPU types or define your own custom VM type shapes using the custom machine type feature. Here's a tip. Custom machine types let you define exactly how many vCPUs and how much RAM you need, so you don't overpay for unused resources. So these are standards. I see custom. I don't see custom available. That's okay. Advanced. You can do a little more customization here. That's okay. All right. F1 micro and E2 micro. Okay. Where are these? Did I see them? I don't see these here. That's sure. Okay. Well, not every task needs horsepower. For those light background jobs, dev sandboxes, or tiny services, Google Cloud offers micro instances. They're small, but they're smart. F1 Micro and E2 Micro are machines ideal for internal cron jobs, low traffic websites, API gateways, or Internet of Things data collectors. These machines support CPU bursting, which means even though their base performance is low, they can temporarily spike in CPU usage when needed without having to scale up permanently. These micro instances often qualify for Google Cloud's always free tier, making them perfect for test projects and proof of concept. So they're not here, but I'm not going to try that now. Preset. So here's the custom, and you see the cost right here. Okay. Mega memory machines. I think we went back over here. Finally, for the ultimate in memory density, if you're running workloads that need to hold the world in memory, you've got mega memory machines. These are part of the M2 ultra high memory lineup and offer up to 12 terabytes of RAM per VM. Common use cases, massive in-memory databases, real-time fraud detection platforms, genomics and biomedical simulations, SAP HANA, scale-out clusters. These machines are sole tenant capable and often run on Hyperthread Intel Xeon platforms, giving enterprise apps both security and predictable performance. So choose the right VM type. So let's do a quick recap. Your standard is going to balance CPU and memory. These are good for web apps, dev environments, and small databases. You have high memory, which are good for RAM heavy applications like in memory databases or analytics. You have high CPU, which are optimized for compute heavy tasks. These are good for rendering, machine learning inferences, and continuous integration builds. And you have micro instances, which are good for light workloads with CPU bursts. These are good for smaller jobs like cron jobs or low traffic services or websites. And you also have mega memory. These have massive in-memory processing. These are good for SAP HANA or biomedical simulations. For the exam, your machine type choice directly impacts cost, performance, and even SLA eligibility. So it's crucial to align your application requirements with the VM profile, and don't forget to monitor and resize as needed. VM images and creation. When you build the foundation of compute, in the world of compute engine, virtually every machine begins with an image. You can think of a VM image as the blueprint, a starting point that defines everything from the operating system to the configuration and base software packages. Whether you're launching a dev server, a database, or a hardened analytics node, it all starts with picking the right image. Let's ignore the different kinds of images Google Cloud makes available to you and how to use them effectively. Types of images. There are three primary sources of images in Google Cloud. Public images. So let's see. Hmm, Okay. Here's the images. Wow. Okay. You'll see your images here. Okay. You have three types of images. All right. Public images. These are official OS images maintained by Google or well-known open source communities. These are always up to date with the latest security patches and optimized for Google Cloud infrastructure. Examples include Debian, Ubuntu, and CentOS for general Linux use. You have Red Hat Enterprise Linux, RHEL, and SUSE for enterprise workloads. You have Windows Server versions like 2012 R2, 2016, and 2019, all licensed through GCP. And then you have container optimized OSs, which are lightweight images designed for running Docker containers securely and efficiently on GCP. An exam tip, always use public images when you want guaranteed support, security, and compatibility out of the box. Then you have third-party images. Number two, You need something more specific? Google Cloud Marketplace lets you launch VMs from partner-provided images, often preloaded with tools or enterprise software. Examples include SAP, Oracle, and SQL Server. These are hardened operating system builds like CIS benchmarked CentOS, pre-configured development environments, or machine learning stacks. These may incur additional licensing fees, so always review pricing before launching. On the professional exam, you may see questions about licensing responsibility and image costs. Remember that marketplace images often include license fees baked into the price. And number three, custom images. Your cloud, your way. Sometimes you need more control. Maybe you've created the perfect on-prem image, or maybe your app depends on a very specific configuration. With GCP, you can create your own image from an existing VM, import a disk image from your data center, or build a custom image pipeline using Packer and automation tools. Once uploaded, your image becomes available project-wide and can be used in instance templates, auto-scaling groups, or even shared across organizations. Here's a security reminder. Make sure your custom images are regularly patched. Unlike public images, you are responsible for updating them. Creating a virtual machine step by step. So we've already done this, but let's walk through this one more time. We can create this from machine image, right? Let's see. Filter, name. Does this include them? Say so. Oh. All right, let's go. Let's go back here. So you create this with the name, right? Use a consistent naming convention like dev slash Jules slash one or prod slash database slash east, right? Select your OS image from the public, the third party, or custom images. If you're automating via Terraform or CLI, reference the family or exact image ID. Pick the region or zone, right? These are specific data centers. Select based on the latency requirements. So you want it to be near where you want it to be deployed. You want availability zone replication, and then you want resource quotas, right? Remember for the exam, Compute Engine does not auto-replicate VMs across zone. That's up to your architecture using instance groups or managed failover. So you have to start updating that within this. Let's back up. Replication, boom, synchronous replication, cross-region, asynchronous, that's where you go. Okay? And then you can add GPUs, right? Why am I not seeing this? I don't see it. Well, here's GPU-based images. All right, so if you're doing this, you can use, yes, if you're doing if you're doing machine learning, rendering, or simulation, GCP lets you add NVIDIA GPUs to your VMs. Popular options include, let's see, the Tesla P4 for inference. You can do the V100. Oh, I see they updated to the A100 and H100. Okay. Oh, there's the V100. There we go. Or A100 for training large models. And then you need to just make sure that your image supports the select, or that the image that you support selects the GPU drivers. And then you select your disk size. Okay. Let's see. Oh, there we go. Okay, so you can select your disk size. The default is usually 10 gigabytes, but you can scale it up as needed. All right. You can also attach secondary disks, choose an SSD or HDD, enable auto delete to clean up unused disks when deleting the instance. Remember, persistent disks can be snapshotted, cloned, and resized even while running. Okay, so take a look here. Source types, image snapshot, instant snapshot, right? Balanced, extreme persistent, SSD. You saw that SSD standard. Here's the size. Oh, looks like it between 10 and 100. Looks like this defaulted to 100 because we're on the GPU. That's right. And then you can encrypt it with Google Managed or Cloud KMS provided by yourself. Uh, oh, there you go. Cloud KMS or customer supplied. And then you can add your labels. All right. Within this, labels are key value pairs. All right. And these are used for billing, grouping, and resource management. These tags are also there to control your firewall rules. So if you want to have location, underscores, lowercase, sorry, location, um, North Carolina, right? Team, sec, dev, ops, contact, let's say, email at first name at domain.com, right? Now you can add these and make them consistent across this. Why do you do this? So that you have consistent firewall rules across all of your resources, including your VMs. You can use these to also break down your costs in your billing exports with BigQuery. When you're done with this, and we're going to hit cancel, you hit the create button, and then you're good to go. Once everything is configured, you hit the button. Within seconds, your VM will be provisioned, IP assigned, and booted up. You'll see options to SSH into the instance, stop, restart, or delete it, attach new disks, or view serial logs. Caution. Here's an important takeaway. VMs continue billing until you stop or delete them. Stopped VMs don't charge for CPU or RAM, but attached disks and reserved IPs will still incur costs. Make it a habit to always shut down unused VMs and delete orphan disks to avoid surprise charges. On the exam, remember that deleting an instance does not automatically delete its disks unless auto delete is enabled. Okay, let's see if that's here. Deletion rule. When deleting an instance, boom, delete a disk. With this knowledge, you're now equipped to spin up tailored compute environments, build golden images, or automate massive cloud scale deployments. So, more compute engine features, flexibility, efficiency, and uptime. In a world where uptime, cost efficiency, and operational consistency are critical, Google Compute Engine delivers more than just virtual machines. It offers a powerful set of features designed to maximize resilience, minimize costs, and simplify scaling. Let's explore three of the most important capabilities that every cloud architect should know, especially if you're preparing for the PCA or the ACE or the Cloud Digital Leader exam. You have preemptible instances. Okay. Let's close out of this. Go back. Instance. I don't see the instance types, but let's get here. Let's see if the instance template would have this. I don't see it. Okay. Maybe the overview will have this. Okay, well, we'll go in here a little bit. Let's go back. Okay, so let's go into preemptible instances, right? So you don't need a VM to if you don't need a VM to live forever, maybe you're running a batch job, fault tolerant analytics, or auto scaling spot workloads. Here is the preemptible VM. Okay, let's see if I can find this thing. Here. These are compute instances offered at up to 80% less than the cost of standard instances. Why so cheap? Because they're temporary. Preemptible instances can be shut down at any time by Google, especially if resources are needed elsewhere, and never last more than 24 hours. These are ideal for stateless workloads like CI/CD pipelines, render farms, or MapReduce jobs. But here's the key. They behave just like standard VMs in terms of performance. You just can't rely on them for availability. Google won't warn you when a preemptible instance is going to shut down. Your application architecture must be resilient. use managed instance groups and auto scaling to prevent re-provision automatically. So let's see. This will go. This is the documentation. Oh, okay, shares inference on the cloud. So here you would G cloud compute instances, create VM name dash preemptible. Okay, that's how you must do it. So you have to update this somewhere in the GUI that might be a little bit more interesting. Live migration. Maintenance without downtime. One of the standout features of Google Cloud's infrastructure is live migration. Traditionally, virtual machines are stopped and restarted during host maintenance, but not on Compute Engine. When GCP performs system updates or rebalances resources behind the scenes, it can move your VM across physical hosts without rebooting it. This means no application interruption, no OS restart, no data loss. This migration is seamless, and your system continues to run normally while the move happens. This is particularly useful for database servers, real-time analytic systems, high availability web apps. However, here's the thing. There's a GPU limitation. Live migration does not work with GPUs. If your VM has an attached GPU, it will be stopped during maintenance. Live migration is one of GCP's differentiators in terms of availability SLAs. It enables proactive maintenance without requiring using user intervention. Let's see. Let's go into instance templates. Okay. In cloud architecture, consistency is king, and that's where instance templates come in. An instance template is a saved configuration that defines everything you'd use when creating a VM. Okay. Within this, you can find the machine type and size. All right. Name it first. Tags, labels. Okay. You get the machine type and size. All right. Disk image and size. Network settings and tags. Labels and metadata. Startup scripts and service accounts. Once saved, this template becomes your reusable blueprint. You can use it to spin up identical VMs on demand, create managed instance groups, power auto healing, load balancing, and auto scaling, ensure consistency across regions, zones, or even projects. Templates are not tied to a single region or zone, which makes them ideal for multi-zone or multi-region deployments. Remember on the exam, instance templates are often paired with managed instance groups, aka MIGs. Together, they're high availability, rolling. They let you have high availability, rolling updates, and auto recovery. So let's put it all together. In this scenario, imagine you're building a web scraping system, and you need to launch dozens of lightweight VMs, scrape the data, process the results, shut them down. Cost is key. Uptime is less so. You'd use preemptible instances to keep costs low, an instance template to launch each scraper VM with the right script, a managed instance group to autoscale and replace failed instances, and rely on live migration to keep critical backend services running without interruption. That's how real-world cloud architecture works in action. Resilient, automated, cost-aware, and scalable. With these features, preemptibles, live migration, and instance templates, Compute Engine becomes more than just infrastructure, it becomes a tool for intelligent cloud orchestration, capable of serving everything from hobby projects to global scale enterprises. Okay, let's try this. Let's try App Engine. Okay, so we've talked about virtual machines with Compute Engine. We have granular control over infrastructure, but let's shift gears to something more abstract, more automated, a lot more developer friendly. Welcome to Google App Engine, Google's cloud platform as a service, or PaaS, right? That's PaaS, not PaaS. Why apps? Why App Engine? So in App Engine, the philosophy is simple. You write the code, Google runs it for you. This means no server supervision, no operating systems to patch, no infrastructure to scale. You simply write your application in one of the supported languages, deploy it, and App Engine handles the rest. Whether you're building a small web app or globally scaled service, App Engine makes deployment frictionless and resilient by design. So you have the standard or flexible environments, all right? Oh, these are the two flavors. App Engine does this, and it's important to know both for architectural decision making and Google Cloud certification exams, right? Standard. Standard runs in a sandbox container. It's fast startup, it's auto scaling, and it's per second billing. It uses predefined runtimes like Python, Go, Java, Node.js. It's stateless by design, and it's ideal for something like web servers for APIs or APIs with bursty variable traffic. So on the exam, remember standard environment is highly optimized, and each instance scales up or down almost instantly based on incoming requests. Okay, flexible. Flexible, it runs in a Docker container on Compute Engine VMs. It can scale slower, but supports custom libraries, longer execution times, and more memory. You can bring your own runtime. It supports SSH access for debugging. Think of flexible environment as a bridge between App Engine and Compute Engine. You get more control, but you also get to take a little bit more on the management responsibility. All right. So regardless of which one you choose, App Engine has some incredible automations built in. Let's see if I can find. Oops. Oh, why that was trying to say. What would this be? Not gonna be here. Okay, but these are built in. So when you go in, let's see. All right, let's go. Get started. Python and created. Choose some. Oh, it works for you. Standard. Chose this for me. Yeah, instance is deleted. I got you. Where is the? I need to learn. Try. I don't want to go to Cloud Run. No, I already downloaded this though. Hold on. Why am I missing this? Get started. Oh, so copy. This command takes you through the configuration. Deploy to App Engine. You app deploy. I don't have an app. Configuration with the new settings. So I'm gonna Control C out of this. I'm gonna kill that command. Um, okay, but within this, there's built-in scaling and load balancing. Regardless of which environment you choose, App Engine has some incredible automations built in. Auto scaling adjusts the number of instances in response to real-time load. Traffic splitting lets you direct a portion of traffic to new versions for testing. Great for canary deployment, blue-green, etc. Built-in load balancing to ensure even distribution of requests. You want to do 90-10, 80-20, however you want your traffic routed, right? This is ideal for teams that want high availability without building it themselves. And yes, App Engine integrates with cloud logging and monitoring, so you can observe your app's health without third-party tools. But you can also use third-party tools too. With App Engine, security is an important factor, and Google has it handled. With this, you have security updates and patch management that are automated. This includes operating system level patches, language runtime patches, that Python, that Node.js, that Go, protection for common vulnerabilities like buffer overflows or memory leaks. App Engine also supports IAM roles, so you can fine tune who can deploy things, view logs, or modify traffic settings. And you have custom runtimes with Docker. Within this, if your app uses a custom language, a non-standard version of a library, or is a complex dependency, App Engine's custom runtime has the support that can cover you. So you can create a Docker file, specify your base image, and deploy it. You use this when your app can't be easily expressed in App Engine's standard runtime model, or if you're migrating from an existing Dockerized workload. The lifecycle, the version control that's built in. Every time you deploy a new version, App Engine retains old ones. You can roll back to a previous version instantly. You can roll back to a previous. Sorry about that. That was Siri or something. I don't know. Split traffic across. You can roll back to a previous version instantly. Split traffic across multiple versions for A/B testing. Route requests based on cookies, IPs, or random selection. It's like a version control for cloud deployments with zero downtime. So here's some example use cases. App Engine signs of workloads like API backends for mobile or web applications, web front ends that need scaling, scheduled tasks or cron jobs, multi-version testing in production environments. Whether you're building an MVP, minimal viable product, or scaling to millions of users, App Engine grows with you without infrastructure stress. So, for the exams, you'll need to know the difference between standard and flexible, when to choose App Engine or over compute or cloud functions, how App Engine's auto scaling, traffic splitting, and versioning are implemented and why. And you can expect scenario-based questions at tests, App Engine versus Kubernetes Engine versus Cloud Run. Security implications like IAM versus firewall, audit logging, and the cost trade-offs between stateless scaling and custom runtime flexibility. So, with App Engine, Google invites you to stop thinking like a system as admin and start thinking like a pure developer. So no servers, no scaling headaches, no patch Tuesdays, just code, deploy, and serve at global scale. Okay, next up, we'll go to Kubernetes Engine. Okay, close this. Okay. Um, all right. Now that we've explored how you can run virtual machines with Compute Engine and how App Engine helps you focus on code without managing infrastructure, it's time to talk about something more modern and scalable and more production ready for microservices, containers. So here's where we go to Google Kubernetes Engine or GKE. What's GKE? GKE is Google Cloud's managed Kubernetes service. It gives you everything you need to deploy, scale, orchestrate, and deliver containerized applications. You can do all this without having to install or operate Kubernetes yourself. If you ever worked with Docker containers locally and thought, how do I manage hundreds or thousands of these across distributed systems? Kubernetes is the answer. And GKE is how Google Cloud delivers it at enterprise scales. All right. So every GKE deployment starts with a cluster. The cluster is made up of two types of components. All right. Let's see. Let's go here. Okay. There's a control plane and the master node. Excuse me. The control plane, also called the master node, manages the whole system. This schedules workloads, monitors health, and manages state. And then there's worker nodes. And these are powered by compute engine VMs, which actually run your containers. Okay? So think of control plane as your mission control. It receives commands, plans what needs to happen, and orchestrates the worker nodes accordingly. So on the exam, you'll see the control plane is fully managed by Google. You don't pay for it in autopilot mode, and you don't maintain it directly. Google handles the high availability, the upgrades, and failovers behind the scenes. Okay. So you see this all here? Cluster, fleet registration, standard versus enterprise. You have to enable that. Okay. Node images. Each GKE node, essentially a compute engine VM, runs a base image. You have two main options. You have a container optimized OS. It's a lean, secure operating system built by Google for running containers at lightning speed. It boots quickly, has a small attack surface, and comes pre-configured for Kubernetes workloads. Or you have Ubuntu. This offers more flexibility. Use it for your workloads that need more control over the system packages, dependency, or debugging tools, right? So basically lightweight versus more secure. The container optimized is more lightweight. The Ubuntu is heavier. Here's a tip for the exam. Choose the container optimized OS for production workloads, focus on performance and security. And Ubuntu, we need package customization or dev tooling. So maybe I had that inverted. Okay. By default, container storage in Kubernetes is ephemeral, meaning if a pod crashes or is rescheduled, the data disappears. To persist data, GKE allows you to attach persistent disks. These are block storage volumes that survive restarts, node failures, or scaling events. These are ideal for databases or any workload with state. You can dynamically provision these using persistent volume claims, PVCs, and GKE manages the underlying lifecycle. Okay, let's see if we have this here. Must not be here. Let's go back. Clusters. This will be applications. Okay. Storage. System volume claims. Okay. Kubernetes in action. So what does Kubernetes actually do for your applications? Let's break it down. It's self-healing. Kubernetes constantly monitors node and pod health. If something fails, it reschedules it elsewhere. It's auto-scaling. Based on CPU usage or custom metrics, Kubernetes can scale up pods or down to automatically. Right? This is a bonus for you. Had a brief break. Okay, so auto-scaling based on CPU usage or custom metrics. Kubernetes can scale pods up or down automatically to meet demand. Load balancing. Kubernetes assigns a stable internal or external IP and routes traffic evenly across replicas using built-in load balancers. Rolling updates. Want to deploy a new version of your app with zero downtime? Kubernetes handles rolling upgrades, allowing one pod at a time to be replaced and verified before continuing. As a bonus, GKE supports blue-green deployments, canary releases, and even A/B testing using Kubernetes native tools. Monitoring and logging with cloud operations. This is formerly Stackdriver. Observability is critical in production. And GKE integrates natively with cloud logging and cloud monitoring. You get out-of-the-box dashboards showing CPU and memory utilization per node and per pod, Kubernetes event logs, health status of deployments and clusters, alerts when thresholds are crossed. There's no need for third-party agents. You can just deploy and be covered. You also have node pools, which are customized by the workload. A node pool is a subset of a worker node within a cluster, all with the same configuration. Why use them? Because not all workloads are created equally. But maybe your app has a front end that needs low latency but minimal RAM. Meanwhile, your back end might be doing machine learning inference and needs high GPU or memory specs. With node pools, you assign workloads to the right kind of hardware, minimizing waste and maximizing performance. There's a tip. Use taints and tolerations or node affinity rules to control which pods can run on which node pool. Okay? So there's GKE modes, like standard versus autopilot. And Google gives you these two ways, right? Standard mode, you manage the node infrastructure, you control machine types, upgrades, auto repair policies, and billing is per node. Autopilot node is Google manages the nodes entirely. You only pay for CPU, memory use that you use in your containers, not the VMs underneath. Autopilot is great for teams that want serverless style simplicity with Kubernetes level control. Please know the difference. Expect questions that ask when to use autopilot versus standard, especially cost sensitivity, high scale, rapid deployment environments. Okay. So wrapping up GKE, you're not just getting container orchestrator. You're getting Google's own battle-tested version. The same tech used to power YouTube, Gmail, and search. And the best part, you don't have to manage the hard stuff. GKE delivers the power of Kubernetes with the reliability, scalability, and simplicity of the cloud. Now, cloud functions, event-driven and serverless. As we close out the exploration of the GCP compute services, we'll come to the most elegant of this and possibly the most invisible. Tools in the Google, this tool is cloud functions. This is where your infrastructure disappears. There's no VMs to configure, no clusters to scale, no containers to orchestrate. You write your code, a few lines or a few hundred lines, and Google Cloud takes care of the rest. Now, what is Cloud Functions? Cloud Functions is Google's functions. Let's see. Let's go over here. And this in chapter 1. There we go. Okay. This is a functions as a service, FaaS or FaaS platform, a fully serverless environment where code runs only when an event occurs. There's zero idle time. You're charged by the millisecond, and you never pay for resources that aren't actively running. You don't provision or manage any servers. There's no patching, no scaling concerns, and no operating system beneath your code. If compute engine is a car, and app engine is a taxi, And Cloud Functions is a teleportation pod. You define what you want to happen, and GCP makes it happen on demand automatically. So, what is event driven design and how does it work? What triggers a cloud function? The answer is literally anything. Google Cloud Functions built around event driven computing. These triggers can come from across your cloud environment, right? A file is uploaded to cloud storage. Maybe it's an image that needs resizing or a CSV that needs parsing. A message arrives on PubSub, perhaps signaling a change in your data pipeline. A new row appears in Cloud Firestore, and you want to send a confirmation email. A log entry changes, say a security alert or a billing event, and you want to auto remediate. Or a new VM instance is created, and you want to tag it or send an audit notification. Here's a little bit of insight. You're not polling or manually checking systems. Instead, Cloud Functions enables reactive architecture, where each service in your environment becomes a source of truth and action. So, the language and runtime support for this. At the time of this, Cloud Functions supports Node.js, which is the default environment, including versions, I think, from 6.11, 10. Let's see. Let's make sure. Let's make sure. Let's make sure. We could do this, but let's get out of this real quick. Let's try to function. So Node.js 6.11, Python, which is great for machine learning, automation, quick scripting, Go, Java, .NET, and a few more, depending on the runtime you select. Okay. Let's see this. Yeah, so yeah, .NET, Go, Java, Node.js, PHP, Python, and Ruby. Those look like what's here right now. Okay. You want to do something low latency in JavaScript? Use Node. Need to parse and load a machine learning model? Python. You can even include third-party libraries in your function package, just like in a traditional app, but scaled infinitely. So how to create a cloud function. Okay, let's go here. Start from scratch. We're in Cloud Run. We'll click on, where is it? Write a function. We can either get a revision from an existing container image. We can deploy from a repo that we're using, right? So, Bitbucket, GitHub, whatnot, or we can create one manually. And we first name it something like resize image on upload, right? Whoops. On upload, right? You set the region, boom. You set the language. Let's do Python. I like Python. Let's do 3.9. Okay. Let's see. The service, number of instances, let's do 2. Okay. And the trigger. So you do, let's say for this, like an image upload, cloud storage. I did select cloud storage, didn't I? Clouds, yes, cloud storage. Okay. Oh, I gotta enable that. So that event, that's enabled. So you need to make sure all your APIs are enabled. Please remember that, right? Event-driven architecture. Okay. Okay. You enable this, you define it. It could be that storage bucket, pub sub, HTTP endpoint, or a Firebase event, right? And then, okay, your networking security is your container information, right? Your memory amount, any arguments you want to have here for the placeholders, any variables or secrets and volumes you want to mount. You can keep going into more detail on this. Once completed, let's see, cloud storage. Okay, there we go. It's here. Okay, you have the trigger name. This could be a unique name. We have the sources and the trigger type. We have the application type. We have the bucket. This should be a named bucket that we've already created. And we'd have to create a service role for this that would have the ability to manage these. And then add the necessary labels. And remember, this is your JSON, right? And Where do you add your code? I don't see it. That's for Google Surface. Oh, that's the trigger type, event provider. Well, that's the event type. It should be. Okay. Oh my goodness. Why am I not seeing the code? Hmm, that's never good. Okay. Hmm. So I'm missing something here. I need to probably go to the next one. Authenticated info require authentication. So this is where I need to create the information here. I don't have any information here yet. Um, at this point, I'd have to, there we go, enter the code here. This is where the code would go. I'd save and be able to deploy this. All right. So what I'm going to do is get out of this. I'm going to leave this. All right. This is just a bare bones template. All right. When you hit deploy, which I did not do, you get a secure URL for HTTP functions or S3 or the storage functions, cloud storage functions, and be able to link this, right? So make sure you know the difference between HTTP triggered functions and background functions. HTTP triggers are direct, and background functions handle events in the cloud asynchronously. Okay. So testing and monitoring. Once deployed, you can edit the code directly in the web console, which I just showed you, trigger your function manually or through the event source. Okay. And monitor execution times, failures, and logs in Cloud Logging. Cloud Function also integrates natively with Cloud Trace, Cloud Profiler, and Cloud Monitoring. So these are tools that go with your APIs, your access, and how you're actually using your resources in the cloud. This gives you deeper observability into your serverless workloads. For production, you set timeouts, retry policies, and security policies with IAM-based execution to limit access. Common use cases would be simplicity, automation, and rapid executions being the essential portions of your job. So in DevOps automation, you could spin up a function that tags new VMs or shuts down orphaned resources. In data pipelines, when a new file lands in cloud storage, parse it, transform it, like resize it, upload, and write it to BigQuery. Security, you detect an IAM change from audit logs, send an alert, or trigger rollbacks, right? If a webhook, right? If you handle an HTTP post request from Stripe, Slack, GitHub, you have instant integrations with minimal code. Or you have an Internet of Things device. If it ingests server data from connected devices via PubSub, it can pass it downstream to BigQuery or Cloud Run. So why does Cloud Functions matter? Cloud Functions let you automate at the edge, build smart, reactive applications, and scale from 0 to thousands of executions without touching a server. It's ideal for developers who need rapid results, architects designing event-driven systems, ops teams building self-healing infrastructure. It doesn't contain events, it doesn't contain containers or VMs, it complements them. Think of it as a glue between systems. You've now explored the different ways that cloud lets you run your applications, whether with full control with Compute Engine, managed scalability and App Engine, powerful orchestration via Kubernetes, or event-driven automation with Cloud Functions. All right. So here's a couple of test questions to give you some thought. Okay. If you have a developer on your team who wants to deploy their application in Kubernetes Engine with a Docker file, they report their application deployments are taking too long. And so you want to optimize this Docker file for faster deployment times without adversely affecting the app's functionality. What actions should you take? 2, use a slimmed down base image like Alpine Linux. And then copy the source after the package dependency, usually Python or pip, right? And these will be installed. So why do you do this? A lightweight base image like Alpine Linux reduces the overall Docker image size, resulting in faster transfers and deployment. And copying the source code after installing dependencies optimizes Docker's layer caching mechanism. It allows for faster builds, when only source code changes, but dependencies remain the same. All right, here's a second question. Think about this. Your solution is producing performance bugs in production that you did not see in staging and test environments. You want to adjust your test and deployment procedures to avoid this problem in the future. What should you do? Slow rollout, right? Deploy your changes to a small subset of users before rolling out to production. Why? This is in that canary, blue, green, A/B testing, right? A canary deployment approaches this by deploying changes to a small subset of users that lets you test changes in a real production environment with minimal risk. This catches performance issues that might not appear in staging environments before they affect all users. Okay. Question 3. Your company has decided to make a major revision of their API to create better experiences for developers. They need to keep the old version of the API available and deployable while allowing new customers and testers to try out the new API. They want to maintain the same SSL and DNS records. What should they do? They should use separate backend pools for each API path behind the load balancer. Why? Separate backend pools behind the API. This allows both versions to be served under the same DNS and SSL certificates. This approach provides a clean separation of traffic while maintaining a single front end for users. Question 4. A small number of API requests to your microservices-based application take a long time. You know that each request can traverse many services. You will want to know which service takes the longest. What should you do? Instrument your application. Use CloudTrace. Why? This breaks down the request latencies at each microservice. CloudTrace is specifically designed to track and analyze request latencies across microservices. It provides a visual breakdown of time spent in each service and makes it easy to identify bottlenecks in complex services. Question 5. Your company is planning to migrate an on-premises MySQL database to Google Cloud Platform. The database currently runs on a physical server with 64 CPUs, 128 gigabytes of RAM. The server CPU utilization averages 45% during peak hours. What compute engine machine type would be most cost effective for this workload? Okay, because the current CPU utilization is 45% during peak hours, you can size the VM approximately to half the current CPU. So if that 64, you could size it down to 32 vCPUs instead of 64. The MySQL database is memory intensive, so the high memory machine type, one of the high mem, that would provide optimal balance of CPU and RAM for the workload. So look for something that's high memory and looks at about 32 on the average. Okay. So you can look at all the different service types: compute engine, app engine, Kubernetes engine, and cloud functions. You can find out what their control amount is, what their management overhead is, what their scaling is, what languages they support, what their pricing is. But you have to figure out what is the right choice. You have to determine control versus convenience. If you need full control, compute engine. Want zero infrastructure management, cloud functions or app engine. State. If you need stateful applications, stateful applications, these are going to work better on compute engine or GKE. Stateless services, app engine or cloud functions. Scaling needs. If you need to handle unpredictable, bursty traffic, app engine standard, or cloud functions, auto scale completely. GKE will provide container level scaling. If you have existing investments, like you already have containers, GKE makes sense. Traditional VMs, compute engine is the easiest migration path. Then you have to look at skills. Teams that are familiar with Kubernetes, GKE leverages that knowledge perfectly. If you're new to cloud, App Engine would be the easiest path. So remember, these services aren't mutually exclusive. The architectures combine different compute services to leverage their respective strengths. You can use App Engine for front-end web servers, GKE for containerized microservices, Compute Engine for traditional databases or custom workloads. You can use Cloud Functions to connect them with event-driven integrations. So, in conclusion, Compute Engine offers Google Cloud's compute options provide an incredible spectrum of possibilities, from complete control to zero management. Understanding the unique strengths of each service, you can design architectures that are resilient, cost-effective, perfectly suited to your application requirements. Whether you're building a simple web app or complex microservice ecosystem or event-driven automations, GCP's compute services offer the building blocks you need to succeed in the cloud. Remember, there's no one-size-fits-all solution. The best cloud architects understand the trade-offs and select the right compute service for each component of their architecture. Now that you understand the engines of Google Cloud, you're ready to power your most ambitious projects with confidence. Thank you. The next chapter will focus on platform storage. This is going to be powering data at scale.